Good evening, profs. I'm Eugene from Group 7 SC04, together with Darius, Sunny, and Kongzheng. This presentation is on our Modeling Space and Systems 1D Part 2 Math Modeling. So, for background context, assuming that cities of the future will be relying entirely on nuclear energy as its renewable source, we expect radioactive waste, which is a byproduct of the above mentioned energy production, to increase substantially. Cobalt 60 is formed when metal structures, such as steel rods, are exposed to neutron radiation. It decays by gamma radiation, which is an electromagnetic wave that causes ionizing radiation that induces biological effects, such as inhibition, stimulation, mutation, and cell death. Although most of the time the waste is well sealed inside huge drums of steel and concrete, sometimes accidents can happen and leaks can occur. The effects of gamma radiation on crop production has been reported by researchers around the world, and we hope to model how gamma radiation can adversely affect factors such as germination and plant growth. Moving on to problem statement. Our problem statement is how would regional factors along with intense gamma radiation emitted from cobalt 60 which are improperly disposed of affect the yield of plants such as sunflowers? We have some assumptions for our math model. Firstly, every city in the future uses nuclear energy to power everything. Secondly, all nuclear waste exists as cobalt 60 isotopes. Thirdly, out of all the nuclear waste disposed of, 10% of them are improperly disposed and exposed to the environment. Fourth, our data for radiation dosage against survival rate is modeled after sunflowers, and we assume that plants with similar traits behave in the same manner. Fifth, all nuclear plants operate at a 93% energy efficiency. And lastly, all inputs from countries that produce nuclear energy and therefore produce nuclear waste.
So, for our independent variables, which would serve as our inputs, we will be using the following. We will be also using the seasonal mean ozone, which is measured in ppm, to factor in the effect of air pollution, in this case ozone, on the plant growth. And this pollution is used to calculate a pollution coefficient of ozone, Pi, and is given by this expression, which is modeled after the study given in the link below. We will also be using the total energy consumption, the land mass of a given country that you're checking for, and the mass of CO60 produced by a nuclear reactor. On top of these, we will also be using the test area of the crop plantation that we will be looking at in this model, or a user will want to look at.
In order to derive the radiation dosage, or GY, we need to do a few steps. First of all, we need to calculate nuclear energy produced per land mass in the country. This is done so by taking the total energy consumption per land mass, dividing by 93%. 93% is the energy efficiency of nuclear power plants. Next, we will calculate the mass of cobalt 60 produced per land mass during production of nuclear energy. This is done so by taking the nuclear energy produced per land mass, multiplying by the mass of cobalt 60 produced by nuclear energy. After which, we assume that 10% of the cobalt 60 are improperly disposed of at each time, which also means that 10% of the cobalt 60 produced by nuclear energy is exposed to the environment per land mass. Afterwards, we calculate the number of atoms of cobalt 60 exposed to the environment per land mass by taking the mass of cobalt 60 exposed to the environment per land mass multiplied by the Avogadro's constant per molar mass of cobalt 60. Then we calculate the amount of radiation energy exposed to the environment per land mass by taking the number of atoms per land mass multiplied by the radiation energy over one atom of cobalt 60. The radiation of one cobalt atom 60 is 1.173 mega electron volts, which is also 1.879 times 10 to the power of negative 13 joules. This will allow us to calculate the radiation energy because now we have the radiation energy per land mass and we can multiply that by the test area and we'll get the radiation energy, which we can use to obtain the radiation dosage by dividing that by the total plant mass.
Ending off the mathematical model, we will be calculating the survival rate of crops using this equation below. This was created to model the results of the ones that is found in the link below. So we will be using the radiation dosage of the plant, which has been already derived in the previous steps, and we will use this to get the survival rate in percentage. Following this, we will also be calculating, as mentioned previously, the effect that air pollution of ozone has on the crop growth. We will be doing this by deriving a coefficient for ozone, which is measured in ppm. So this coefficient is also modeled after a study which has been mentioned previously with the equation below. And O squared simply means the seasonal mean ozone squared, which is one of the main inputs. Lastly, we will be calculating the yield percentage, which is our final output, simply by taking the survival rate of plants due to the radiation and multiplying them by the ozone pollution coefficient. This means that if an area has high radiation dosage, plant has high radiation dosage and has also high air ozone pollution coefficient, the crops will be nearly wiped out, if not wiped out already. Or if one of these were to be too much, let's say there's too much radiation dosage and there's optimal air pollution from ozone, the crop yield will also decrease. And similarly, if there is not much radiation dosage, yet the air pollution from ozone is really high, the yield will decrease. Ideally, both the survivability rate of crops should be high, which means that the radiation should be low, and the ozone pollution coefficient should be 1, which means that the ozone pollution itself, seasonal mean ozone, should be low. So when the radiation dosage and the seasonal mean ozone are low, consequently, the survival rate and the ozone pollution coefficients will be high. And when you multiply these together, you will get the yield in percentage of the crops of sunflowers in this case. So to end it off, before we do so, we would like to verify that there are multiple dependent variables which can be extracted from a model, and these are the two main ones. But within this one of them, which is the yield, is the key output that we are aiming to give, which is derived as what I've previously mentioned. And apart from this, a user can also take out the radiation energy values from the middle of this equation, because we will be doing this in steps in the middle of this model, because we'll be using various steps of equation. So this might be another point of interest that a user may find that he or she may want to use as one of the outputs from a model, which is radiation energy.
Moving on to our model analysis. First, we will be covering the strengths of our model. Our model is consistent with the assumptions that we have made. One of the key assumptions that we have made is that all nuclear plants operate at a 93% energy efficiency. Our model accurately describes this behavior, and therefore we have developed a meaningful solution. Derivation of radiation dosage is simple, and our model is also easy to understand. Our model works for most agricultural plants with similar traits to sunflower as well. Moving on to the weaknesses of our model. Our model is only useful for countries who fully rely on nuclear energy and produces it. The plant species that we have investigated was sunflower. Our model may not be largely applicable to other plant species who do not share similar traits to sunflower. It is also difficult to predict if nuclear plants will be the main source of electrical energy for the future. There are other regional factors that we have not taken into account when considering for this model. We have come to the end of our presentation. Thank you for listening.